Everyone. Today we are going to learn about concavity and points of inflection. Let's look at these two faces on the right. If the curve looks like one of these shapes, then it is considered concave up. If the curve looks like one of these shapes, then it is considered concave down. Previously, we learned that if first derivative is positive, then the original function is increasing. If the first derivative is negative, then the original function is decreasing. If the first derivative is equal to 0, then we have horizontal tangents, and f of x may have local maximum or minimum point if the sign of the first derivative changes from positive to negative or from negative to positive at those points. Today, we are going to look at the sign of the second derivative and what it means for the original function. If the second derivative is positive, then the original function is concave up. And the critical point then will be a local minimum point. If the second derivative is negative, then the original function is concave down. And the critical point will be local maximum. If second derivative is equal to 0, and the sign of the second derivative changes from positive to negative or from negative to positive, then f of x has point of inflection at those points. Let's look at the definition of concave up or down. This is a given curve. So we can draw tangents on that curve. If the tangents stay above the curve, then that piece of curve is considered concave down. If the tangents stay below the curve, then that piece of curve is considered concave up. Where the function is changing from concave down to up, or other cases it could be from up to down, we have point of inflection. Let's look at example 1. For the given graph, on which interval is the graph concave up? Concave down. If you look at this graph from left to right, the first piece is concave down, then concave up, then down from 3 to 5, and from 5 to positive infinity, concave up again. So concave up from 2 to 3, and from 5 to positive infinity. Let's look at part B, where the second derivative is negative. Means original function concave down. So function is concave down from negative infinity to 2 and from 3 to 5. Let's look at part C, where the function is increasing and second derivative is positive. Second derivative positive means original function is concave up. So increasing concave up, increasing concave down, increasing concave up, increasing concave down. So we have 2 to 3. And let's see if we have more intervals. Decreasing concave down, decreasing concave up, and increasing concave up. So from 6 to positive infinity. Let's look at part D. Decreasing and second derivative is negative. If the second derivative is negative, then the original function is concave down. So we are looking for the intervals where the original function is decreasing and concave down. Increasing, increasing, increasing. So it is decreasing and concave down from 4 to 5. Part E, increasing, increasing only. So increasing up to 4. So from negative infinity to, but let's pay attention here because we have horizontal tangent, means first derivative is 0, so we should not take 2. So from negative infinity to 2, from 2 to 4, and let's see if we have more increasing intervals. So this is decreasing, and from 6 to positive infinity, again increasing. Part F, tangents lie above the graph, above the curve. So we learned that if the tangents lie above the curve, then the original function is concave down. Because if you draw tangents, they will lie above the curve. So concave down from negative infinity to 2. This is up, down from 3 to 5. And again, it is concave up after that. All right, so let's look at now example 2. It says, use second derivative test to answer the following questions. This is the given information. First derivative is 0 when x is negative 4. So we will have a horizontal tangent when x is equal to negative 4. And the value of second derivative when x is equal to negative 4 is positive. So positive means original function is concave up. So if we have horizontal tangent there, then that point when x is equal to negative 4 must be a local minimum. So there is a local minimum when x is equal to negative 4. Let's look at part B. First derivative is 0 when x is 3. And second derivative is negative 5 when x is 3. So means it doesn't matter what number we have here. So second derivative is negative. So less than 0. Means original function is concave down. So then we must have a local maximum here when x is equal to 3. So there is a local max when x is 3. Let's look at example 3. For f of x equals negative x cubed minus 6x squared plus 5, use second derivative test to determine max and minimum locations. So let's take the first derivative. So negative 3x squared minus 12x. So to get the x values of local maximum and minimum, we need to factor first derivative. So negative 3x is a common factor, so we get x plus 4. Then we need to find the zeros of the first derivative. So that gives us x equals 0 and x equals negative 4. So we want to know if we have local maximum or minimum when x is equal to 0 and when x is equal to negative 4. But we want to do it not with the first derivative test, but with the second derivative test. So what we can do is that we can take those values and sub in the second derivative function to see the sign of the second derivative. That's what we want to do. But first then, let's get the second derivative function. So we take the derivative of the first derivative. So first derivative is negative 3x squared minus 12x. So we get negative 6x minus 12. So let's substitute 0 in the second derivative. So we get negative 12 here. Means second derivative is less than 0. That means original function is concave down. Then we have a horizontal tangent here when x is equal to 0. Then that point must be local maximum point. We can do the same thing for negative 4. So let's take negative 4, sub in the function. So we get positive 12. So second derivative is greater than 0 when x is equal to negative 4. Means original function is concave up. So that critical point must be then local minimum point. So please check part 2 for the next question.